hari raya kan. Hari raya tak lama lagi, minggu depan. Okay.
Doktor balik kucing lah doktor.
Betul, doktor, betul.
Balik kucing. Ya, balik kucing. Saya faham you guys sekarang ni nak pergi pasar, nak beli barang untuk sendiri, untuk anak-anak. Lepas tu harga, mungkin kain dah habis saiz ke apa kan. Laki lagi lah beli kain, baju yang siap kan. Takut dah habis ke. Ah,
Nak beli langsir, doktor.
langsir. Okay. So, saya faham
Minggu
lah.
depan
Okay.
tak
Sebab
boleh,
tu,
doktor. Minggu depan habis.
you bayangkan kalau kita ada kelas pukul 2 sampai 10. Macam mana bila nak pergi
Betul.
pasar. Okay.
Nasib baik
Sebab
doktor awal.
Sebab kedai buka pukul 10 pagi dan tak mungkin you keluar pukul 10 pagi, saya faham. Dan kita penat lah bulan Ramadan ni. Okay. Nasib baik semua setuju tukar pagi. Okay. So we start and I will be speed up a bit. Okay. So kenapa Khairul raise hand? Oh, lower hand. Okay. So noise.
Tekan doktor,
Yes.
tertekan.
Okay. Okay, tak apa. So noise we have two kind, internal noise, external noise. Internal noise is exists in the system. External is exists outside. We cannot control. Macam lightning, solar noise, ignition, crosstalk. This one is external. Internal noise ada dua. Minimum. You need to see the module. Okay. Saya berharap you beli module tu lah. Kalau tak dapat beli pun uh, sebab modul tu lagi banyak lah information okay. Slide ni insyaAllah okay, tapi maybe tak banyak information lah. Okay. Thermal noise or Johnson noise is random movement from electron. Bila satu device itu increase dalam haba dia increase, temperature dia increase, elektron akan bergerak lagi laju. Bila elektron bergerak lagi laju, elektron yang terlibat dalam pengaliran elektrik atau elektron yang terkeluar daripada dia punya atom atau molekul lebih banyak, jadi akan bertambah aliran elektrik undesired, okay, because of the haba. So that's why this is a noise. So this one is thermal noise or Johnson noise. Nama dia lah. Okay, thermal noise. Sebab tu you tak boleh you pasang kalau handphone haba ke handphone haba tinggi ke apa, handphone you kadang-kadang dia auto off kan, dia bagi tahu warning haba increase. Okay, sebab bila increase haba, increase temperature akan berlaku noise lah dan boleh merosakkan the system lah sebab terlalu banyak noise. Sebab ideally kalau tidak ada increase of temperature, tak adalah undesired flow of current. Okay. Short noise is random arrival of carrier, electron and hole. Okay, this one is short noise, random occurrence lah, macam hole and electron combine. Okay. Electron and hole you dah belajar dalam electronic device lah konsep. Okay. So thermal noise is what I've been explaining just now. It is being induced by the increase of temperature. Okay, by having increase of temperature, there will be a current flows. So it will create current flow. So when there is current flow, there is a voltage. So this create a noise voltage called as the term is NT. So noise voltage is influenced by temperature. That's why called thermal noise. We call it also Johnson noise or white noise or Nyquist noise. Okay. So white noise means white taking over the term pelangi, warna putih. Warna putih ada banyak color. Contoh kan pelangi, jadi white noise is over wide range of frequency. Okay. Kita tak dapat kawal thermal noise ni dekat certain frequency. No, dia macam random. Okay, means white. White noise is macam warna putih ada banyak 7 color. Macam itulah white noise. Maksudnya dia ada across all frequencies lah. And then Nyquist noise. Banyak nama. Okay. So the terms of the thermal noise, the formula is Pn, okay, proportionate to TB, temperature and bandwidth. This temperature in Kelvin, maybe you perhaps have your own T in Kelvin is in this. However, if you want to convert, you want to convert from TK, okay, coming from degree Celsius, you need to plus with 273.15. Okay, baru you dapat temperature in Kelvin. Okay, or you can use calculator. Okay, you should be very well versed with your own calculator. Then you can convert them instantaneously. Otherwise, manually lah. Okay, 273.15. Okay, so contoh kalau you ada 3 darjah Celsius, so T Kelvin at that time is actually 273.15 plus 3, then you will have 280.15 Kelvin. Equivalent to T degree Celsius. Okay. So noise power can be modeled using a voltage equivalent circuit, Thevenin circuit, or Norton equivalent circuit, which you know lah. This one you learn in circuit theory or electrical circuit analysis. Okay, I'm not sure what is the current name lah, tapi that subject you belajar Thevenin and Norton. Okay, power is watt, and then Boltzmann constant EKTB, 1.38 times 10 to the power negative 23. So TB. So this is the noise power. Okay, thermal power, noise power. So bandwidth is measuring in the terms of hertz. Kalau 10 megahertz, so you kena letak 10 darab 10 kuasa 6. Okay. Okay. So the thermal noise, you have this as your RN, resistant noise source. Okay. And then you have voltage noise. So this is how we want to equate them. Okay. So source circuit asalnya bentuk dia macam ni. Okay, ada resistant. Then we equate them to equivalent in order for us to able to analyze them better and simplify the circuit analysis. So we separate them into two, which is RN, the resistant with the noise free, no noise, and then with having voltage noise source. So from one single RN with noise source, it will be broken down into two components for easy analysis in terms of Thevenin with parallel series condition of RN, free noise, and voltage noise. Okay. Some of you have learned also maximum power transfer. We can do maximum power transfer if our RN noise is equals to our RL. So we're going to have RL. Okay. Maximum power transfer is if Rn is have the same value as Rl. So maximum power transfer, for example, kalau you transfer 100 watt sini, so sini dapat 100 watt lah, maximum power transfer. Okay, under ideal condition. So this one is also called as a impedance matching. Okay, so that power transfer to the load lah. Okay, maximum power, concept of impedance matching. Okay, carry over that understanding just now. Okay, so this is your load. Saya dah lukis tadi. So for maximum power transfer, okay, we try to see what is our VL. Okay, so using voltage divider, okay, you have this one is RL. Okay, over the total resistance in the circuit, RA plus RN, over the noise voltage. Okay, then you get Vn over 2. How you get Vn over 2? Because Rl is equals to Rn. So it's 1. Let's say it is 1. Let's say we assume Rl is equals to 1. Okay. So Rn is also equals to 1 because they are the same for maximum power transfer. So this one is 1 plus 1 Vn. So that's why you have Vn over 2. Okay. So again, for maximum power transfer and for us to calculate the power delivered to the load, okay, so you have VL squared over R, okay. However, this one is, we need to change into VRMS value. So VRMS value, Vn over square root of 2, okay, VRMS over R, okay. So that's why you have this Vn square, Vn square. Oh, I missed another term. Sorry, this one. I missed two. Okay, two here. Okay, sekejap saya ulang balik. Saya miss the two. Okay, so VL square, VL not VC, VL square is Vn over 2, taking from here. Okay, and then square root of 2, it's 2, because V square over 2 is the formula for power R. And then from the Vn to, actually the Vn is actually, you just times by 2. Okay, Vn square, Vn over 4, and then 4R, and then R. Okay, then rearranging, you will have Vn square over 4R. Okay, so this one is already means maximum. Okay, already means maximum. Kalau dia VRMS, we need to convert accordingly. Okay, because this one is V maximum. Then Pn equals to PL equals to KTB. KTB is what you learned just now. Okay, the concept of noise power. So P noise equals to P load. Ideally, they are not the same. However, for maximum power transfer, they are the same. Okay. Again, Pn is not always the same with PL. This one only the same if maximum power transfer happen. Okay. Maximum power transfer from the source to the load. They are not always the same. So soalan kadang-kadang kena tengok betul-betul lah, takut dia ada tricky. Okay. Tapi insyaAllah hopefully not lah. Okay. So Vn, so this one is the power. Then we equate to the PKTB. And if you arranging, you will get Vn equals to 4 KTBR. Okay. Bowman's constant, temperature in Kelvin, bandwidth in Hertz, resistance in Ohm. If the resistance, if not mentioned, okay, if the resistance is not mentioned in your question, it is assumed as 1. Again, if it's not mentioned, it is assumed as 1. Okay. Kadang-kadang dia bagi tahu, kadang-kadang dia tak bagi tahu. Kalau tak bagi tahu, satu lah dia. So for KTBR, the one operational op-amp with frequency range of 18 to 20 has input resistance of 10K. Calculate noise voltage. Operate at ambient temperature. So you have 4. 4 is number. K is constant. You can use your calculator. T is actually in Kelvin. So because they give 27, so you need to convert them plus 273.15 or 273. It's okay. And then you have bandwidth is given. Bandwidth is this one, but this one is higher frequency 20. This one is lower, so you need the bandwidth is actually 20 minus 18. So you have 2 megahertz. 2 times 10 to the power of 6. That's why you have this. Okay. Then you have Vn equals to 18 microvolt. Don't forget the volt because it is a voltage. Don't forget the unit. Okay. And then signal to noise ratio. So signal to noise ratio is a ratio between the signal and noise. Sorry. So by the ratio itself, you know that if you have more signals, SNR will be better. Means increased SNR is good because in that condition, maybe the signal is actually higher compared to the noise, or signal is doesn't change, but the noise is smaller. So we want the SNR to be bigger, okay? Because signals to noise ratio, the noise is smaller, okay? Then signal SNRO is SNR output, signal to noise ratio at the output of the system, and SNR input is the signal of noise ratio is at the input. So by understanding, signal to noise ratio is always less than input is logic because our input normally higher lah. Okay, our input power. So signal to noise SNRI is actually signal input signal over uh, input noise. Okay, which normally higher than our SNR output SO over NO. Okay. In the receiver usually constitute a process called uh, filtering, demodulation, and amplification. Don't worry about this. We'll go through this in another chapter. Other parameter that can be used are noise factor and noise temperature. Okay, we will go through this now. Okay, the noise factor is the linear term. Okay, the noise factor is the linear term of the value. Okay, and then the decibel equivalent, we call it as a noise figure. Okay, so depends on how you write. Okay, for example, if you want to use noise figure as F and noise factor, if you want to use noise factor as F, maybe you can use noise figure as and F. Okay, but for me, when I'm marking your paper, I just want that I understand what you want to do. So noise factor in the linear term, this one is in linear, nombor saja, is actually a ratio between SNR input over SNR output, this one. So if you want to rearrange further, S over Ni, okay, bagi divide by S over No is actually, okay. So sini, sino, niso, okay. And then the noise figure NF is just simply the 10 log of noise factor, okay. So this one, SNR, if you have the SNR, so it is just 10 log, okay, 10 log of the SNR. So this SNR can be SNRI, like what we saw just now, or it can be SNR 0, okay. Okay, so this one is one of the favorite question asking in test. One of the favorite question asking in test. In fact, it has been asked in the Perdana test, test 1 last semester, okay. I will share it to you maybe so that you can see how the question look like. Okay. I have shared some of the test question at the end of the slide, but I didn't share the reason test 1 of the last semester of our mainstream cohort. Nanti you tengok. Okay, I will share them. Okay, so so this is the noisy amplifier. What does it mean by noisy amplifier? Bukan amplifier to be seen. It's actually amplifier with having noise. Okay. So this is the input noise. Okay. This is the noise of the amplifier, and this is the gain of the amplifier, and this one is the output noise. Remember, we are dealing with noise calculation. So we don't dealing, for example, what is the voltage output, what is the input voltage of the amplifier. No, this chapter is actually, this section is only about the noise. Kalau tak, memang ada value lain ni. Okay. Contoh, you hantar 1 volt, you kena ada 2 volt of you ada 2 volt keluar, means amplification is 2. But now, we don't discuss about that. We just discuss on the perspective of noise. Okay. So, if you see, the amplifier have its own noise, okay, which is NA. Sometimes we can take this one out for easy calculation. You take this one out. Okay. When you take this one out, it become NE. Okay. You take this one out, it become NE for easy calculation. Where NE is actually um, NE is actually a ratio, a comparison with your NA. Again, NA is being taken out. Means NA is already with the gain. NE is not without the gain factor. Okay. So NA is actually equals to G NE. Okay. NA is equals to G NE. Because it has been taken out, means it is not being amplified with a factor of G. Okay. So if it's inside, it's already with factor of G. So that's why if we want to do rearranging, NE equals to NA over E. Inside you have this. Okay. And then power, that's what you learned just now. Power equals to noise power, input noise, so equals to KEI. Okay. To calculate for the output noise, okay, output noise is coming from coming from here and coming from here. Okay. So noise output equals to um, G gain of Ni. Okay. G equals to Ni and G later we relate with this. Okay. And output equals to G Ni. Okay. Plus Na. Okay. This Na is assuming it is still this one. Okay. However, we take them out later. Then it's become G Ni plus. Remember this one? G Ne. Okay. Because gain is actually similar. So you just take this one out. Then you have Ni plus Ne. So since noise is power, so it is actually in the form of what? Unless you make them decibel, so you need to apply 10 law. Okay. So this is pretty much I think in the slide. I hope. Okay. If it's not in the slide, is it in your slide? You can take this photo. Okay. This one is when I'm explaining to the student, but this one is the concept. Okay. See no and see so. Okay. Just rearranging. I have shown briefly just now. Okay. So the next is actually we have um, further exploration. Okay. Further extension of the concept of noise. Okay. So now we have include the signals. Okay. Just now we didn't include the signal, right? We only see the noise. Okay. We didn't include the noise. Just we didn't include the signal because we want to dedicate solely for the noise. Now we introduce the real one with the having its own value. Lah. So signal to noise ratio at the input is equals to signal to noise ratio at the input SI over NI. This one is pretty straightforward. Okay. And then S and RO is achieved from SO over NO. Okay. Remember just now we learned it is actually G equals to Ni plus Ne. So that's why you have this. Then this one is SO having amplified by a factor of G for a signal of Si. That's why you have this one. And then rearranging and removing the common terms. Okay. So this is common. So okay, and then this one is also, so you remove them, then you end up with only having this. Okay, then further simplify. Ni over ni is 1, and E over Ni. So this is your noise factor. Okay, SNRO is always less than SNRI. This one has been informed to you just now. Input, right? Output is normally less now. So we have extending from the concept of the noise voltage, we are carried over to the concept of temperature. Okay, so for the temperature, F, okay, taking over similar understanding, 1 plus TE over TI. Okay, TI is input temperature, TI is the ambient temperature, and TE is the temperature of the device lah. Okay, so 1 over TE. So if you want to do rearranging, TE is equals to noise factor, noise factor minus by 1 over ambient temperature. TI is ambient temperature, temperature of the sekeliling or the input temperature. Okay, so that's why you are being introduced to this. Okay, so I'm not sure if you have this with you or not. Okay, but I have shown just now briefly what you have. Okay, this is the noise factor, and to make it the noise figure is just 10 log. So the answer will be in dB. Okay, so exercise 3. Okay,
Doktor boleh share yang tadi doktor, yang sebelum, yang tadi.
yang sebelum, sekejap
Ah,
Ni ke?
saya betul jap doktor. Okey doktor. Betul.
Okay. Tulisan saya yang cantik ni awak faham lah. Okay. So noise generated in amplifier, the word here noise generated in amplifier, maksudnya di dalam. Okay. Of 5 MHz bandwidth is represented by amplifier input noise power of 0.082 picowatt. Calculate noise factor and noise figure if the amplifier was fed with source input signal match the temperature 300 K. So ini direct forward saja, straightforward. Okay, because it's KTB here, you just masukkan sajalah. Ni exercise actually, that's why it's kind of not that challenging lah. Okay, so but good for your understanding build up. 138 times 10 to power of negative 23. Temperature is given in Kelvin already, so masuk 300. And then bandwidth pun dah dibagi tahu 5 MHz, nampak tak? So 5 darab 10 kuasa 6. That's why you have this. Okay. And then ini ialah you punya noise power. So soalan tu minta noise factor dengan noise input. Okay. Sini sepatutnya tukar noise power lah. So sepatutnya ada satu soalan lagi noise power. Okay. Okay. So noise factor is given noise factor F saja. Noise factor kita dah tahu tadi formula dia Ni plus Ne over Ni. Okay. So Ni is the ambient noise. Okay. Ambient noise. Dia dah bagi tak? Okay. So this is your input noise. Okay. Input noise. So this one is your Ni. So you masuk kat sini 0.02 plus NP plus NE, okay, the noise generated in amplifier, okay, so 0.082 over 0.02. So you dapat the value 4.9, okay. Then the noise figure is just 10 log of this lah. Then you get 6 dB. Okay. So similar understanding. Just repeated lah. Question sama, so tukar nilai je. Dapat lah. Okay. So noise factor and noise figure were higher when operated at lower room temperature. Okay. Noise factor and noise figure were higher when operated at lower room temperature, suggesting that S and R is much larger than S and R compared to the previous case. So this one is actually the conclusion made from two questions. Because if you see the first question, the A, higher temperature, and then after that it's cool down. So with this you can see at 300K, you get noise power. At 300K, you get noise figure at 6 dB. Okay, sorry, at 7 dB. And then at 100K, you get noise figure at 11. So when you have lower temperature, the noise is higher. Okay, for this situation lah. Okay, next is this one is straightforward. I want you to try this at home. Okay, this one is just straightforward. It's just extension. Okay, kalau you tak dapat bagi tahu saya lah. Okay, saya tahu you punya slide tak ada jawapan. Saya dah cover jawapan tu actually, tapi saya buka masa saya present lah. Sebab ada intention saya nak student cuba dulu sebelum dia tengok. Okay. So then we have the next one is cascaded communication, cascaded connection. In communication system, cascaded connection is commonly used lah. Cascaded ni macam you nampak macam ni, macam Seee lah. We have pre-amplifier, demodulator amplifier, disusun Seee. Okay, this one what we call sometimes cascaded lah. Below is example of cascaded connection. Input signal, input noise power, input temperature, and then the noise of the amplifier NE1, and the noise of the demodulator NE2, and the noise of amplifier NE3. F1 is the noise factor of amplifier of pre-amplifier, and TE1 is the temperature of the pre-amplifier. And the same understanding for the demodulator and the G3 lah, amplifier. So you have, if this is input noise, input signal, no input noise, input signal, then you have output noise. And then you have input noise, then you have output noise. Okay. So this one is cascaded connection. This one is from the understanding just now. Okay. So we have S1 equals to G1 plus SI. Okay. Easy for one connection. We have one connection only. S1 equals to G1 times S1. And then for the noise is N1 plus G1 NE1 plus G1 NI. And then you expand the N is actually equals to KTB. Okay. And then you will do some factorization. G1 KB equals in bracket TI plus TE1. So cascaded connection is this. You just add another element and you just multiply them again. So if you have S1 here now is input to the demodulator. So that's why S2 is equals to G2 S1. That's why S2 equals to G2 S1. But we remember that S1 is actually G1 S1. That's why you have G1 S1. Okay, so it's just expansion. And then the noise is actually N2 equals to G2 N1 plus G2 N2. Okay, G2 N1. So this one you have this one. Okay, factorization and then expansion because for N1 is this. So this one you just expand them and then you have this. So don't worry so much because it's just simply expansion. Okay, and then the same goes for the concept of the third cascaded element. You just expand. So because G3 is actually the gain of all, so uh, and then S2 is you take from the previous one. So S2 go to here. Okay, and G3 is the amplifier of that last component lah. So okay, where's the G3? This one. Okay, bulan puasa memang mencabar juga mengajar. Yang mendengar pun mencabar juga nak digest. So this one is just expansion. So nothing menu apa putar apa berikan bengkok sini is just very straightforward. It's just expansion of the system lah. Very much straightforward. And then F total here, why we use the word F total? Because we are considering 3 elements total, not single element. So that's why we use the term total. And then SNR input over SNR output. So this one is pretty much straightforward. SNI at input. However, at the output, you need to expand it, just like where we go through from the previous slide. Okay. So SNI, S is okay. NI is equals to KTB lah. And then the NO, okay. NO is coming from this slide just now. You see? Okay. This one you have this NO. Okay. Over, and this is your NO. And this is your SO output. Okay. And then if you notice, you can make cancellation. Okay. If you notice, you can cancel out those that actually common terms. Okay. So you can cancel out K, of course, right? You can cancel out K and so on, leaving you only the terms of this. Okay. Remember B also can be buang, customer. Okay. So end up you have this. And then we have 1 plus T over Ti. And therefore, for 3 cascaded, you will have F1 plus F2 minus G1, F3 minus 1, G1, G2. So from this understanding, we can see from this equation alone, you can see that for system with cascaded connection, you can see the noise, okay, the noise contribution, the noise factor calculation, you can see from this equation, the first device or the first device in the system contribute to the most noise, okay, or if it's low, it contribute to the lower noise of the entire system. Because for the other level of cascaded device, they are being shrink down by G1, and G2. They say we have 4 cascaded system. So we have 4 minus 1, and then G1, G2, G3, and G1, G2, and G3. Okay. So this is noise factor. Okay, let's say you have noise factor 10 dB, for example, 10 dB. So you have to use linear term because this one is noise factor. So 10 to power of 10. Let's say this one is 3 dB, for example. So you need to change them to linear. How do you change to linear? 10 plus 3 over 10. So this is the linear. This formula should be using linear solution. Okay, means the gain also need to change to linear term. Okay, let's say gain is 2 dB. So the linear term for gain is 10, 2 over 10. So you get 10 to power of 0 0.2. You get one answer. Okay, so this one is linear term formula. So the next is a freeze formula. Okay, maybe I skip the third race sebab I try to help everyone and myself so that we can finish earlier lah. Okay. Okay. Total noise figure. Uh, because okay, this is the total noise figure. So from the noise factor, you can convert to the noise figure just using 10 log of f. Okay. So f. Oh, this is f. Okay. Then total noise temperature, the first, again, the same similar concept, TE1, and the next of the noise temperature, it is being reduced by factor of G1, G1, G2, and so on. So you see, this one is always lesser than 1. So that's why for the four cascaded system just now, the last term is T4, but G is actually G3. And until I said, okay? So this formula was in linear, like I told you. Value of SNR F loss gain normally given in dB, we need to convert to linear first, like I told you just now. We need to convert, okay? Linear passive device have noise figure equal to their loss, okay? Linear passive device is, for example, resistor. Resistor is linear passive device. What is the non-linear device? Transistor, but transistor is active device, okay? But it's non-linear. Okay. So we have the examples, okay? You are given ABC amplifier connected in series, okay? Amplifier A, B, and C. So amplifier A is GA equals to 20 dB, and then FA is equals to 3 dB, and so on, okay? An input signal of 50 dB higher, the noise level was fed at the input. So what does it mean by 50 is level higher is SNRI is equals to 50 lah. Okay. Higher than noise level, 50 divided by 1. Okay. So calculate the total noise factor and SNR output. So because it's 3 cascaded device, so you have F1, F2 minus 1 over GA, F3 minus 1 GB, GA. Okay. We don't have. So from this understanding as well, you can see the gain of the last devices does not contribute to noise, okay, or noise calculation, okay, because you see you didn't have GC here, right? Okay, so that's why when question asking you maybe what you can suggest or what you can recommend in order for to improve or to reduce the noise, then your answer can be using the first this one F1 lower the lowest, or you can increase the gain. By having gain increase, this term will be reduced, so the noise will be smaller. So noise figure is 10 log 2.0.3. Okay, you get 3.05. And then given SNR in 50 dB, just like now. Just now I told you. So FDB is equal to SNRI minus SNRO. Okay. So this one, I think that I just want to refresh your mathematics, okay? Because this one is divide, okay? In the log term, in the log term, if it is divide, for example, log A minus B, if you want to rearrange, it will become log A minus log B, okay? Something like that. So that's why you have this one like this, okay? Because dB is log. That's why you have minus, okay? Then 50 minus 3.05. So you have output SNR is equals to 46.95. Okay. So next is noise in modulation system for the additive nature. Like I told you in earlier lecture, noise is additive in nature. So you have random noise output output noise become ST plus NT. Okay. So what noise is a constant PSD, power spectral distribution, PSD. If I am mistaken, PSD is spectral distribution for all frequency. So that's why we call just now I told you right white noise because it happened at all frequency. So this is white noise. Okay. Gaussian noise voltage amplitude are assumed to have a Gaussian distribution. Um, This one not really covered. We only, in fact, only have Gaussian noise in this chapter only. Okay. Next, we have a band limited noise. The noise is limited to certain band following the application used. Okay. Any application system that use modulation typically have a band pass filter at the front end of the receiver. This one. Band pass. So by having band pass, we limited our noise and also our signal at certain range. Yang lain, maksudnya yang lain, the other outside of that frequency range, the signals or the noise or both of them will be uh, degraded or attenuated. Okay, filter only allow the signal within this first allows frequency range only. Okay. However, because this filter is only removing other noise at other frequency, means it didn't remove the noise in the frequency range. So the noise is still exists. That's why it's not able to recover directly. Bypass representation. This one is good to know. I don't want to go. Good to know. Okay, means maybe not really. You don't need to really go through on this. Okay, this one is good to know. Maksudnya bila saya bagi tahu ni, mungkin tak tanyalah dalam soalan Okay, sebab this one is just good to know. Okay. Noise in modulation system. This one is also good to know. Okay. PS. This one is also good to know. Okay. Uh, uh, Good to know. Okay, so I don't want to cover so much Okay, sebab kita fokus kepada yang akan ditanya lah. Okay. So this is actually the questions from the module that I've taken. Okay. I show the screenshot here for you. Okay, the photo. I hope that you will try. Okay. Okay, the circuit is noise free. Okay, this term, the circuit is noise free. Let's say the word. Sometimes we mention the word here. Maybe we mention the word negligible. The noise is negligible, or it is free from noise. Okay. So what does it mean by this? In the calculation of the noise factor. Okay. So if the noise is free, uh, okay. So if the noise is free, where is my okay? So if the noise f is equals to one, okay. If the device is free from noise, so noise factor is equals to one, and f is equal to 10 log one. So you get what? 10 log one. You press your calculator, you get zero. Okay, noise figure zero. So the device that having free from noise, if you put the f noise figure factor one minus one, so it's become zero because there is no noise free. Okay, that's why device that having free noise or negligible noise, that's why f equals to one. This one I shared as well. You can see them. Okay, okay. So now habis dah chapter 1. Hmm, we'll start around 12 lah for chapter 2. Okay, we start at 12.